A little over a year ago, I put out a video on how you can make alum from different types of drain cleaner and aluminum foil. The video performed a lot better than I was honestly expecting it to, and I got a ton of requests for a follow-up, which was again pretty unexpected for something seemingly so simple. However, when I finally got around to reading about alum for a possible follow-up, I found that the scope of possibilities was at first immense, and frankly a bit overwhelming. As a result, working on this video ended up being one of my most involved and long-running projects, and spawned 4 other videos from things I learned along the way. To that end, today I'm going to show you what I learned so far, along with all the alums I was able to make with what I had on hand. This video is a bit of a monster in concept, as the scope included the entire periodic table, so try and stick with me through this first part, and I promise things will get a lot more interesting. So, at the very simplest level, the word alum refers to the hydrated double salt of potassium aluminum sulfate, which is what I made in my first video. This classical alum was discovered thousands of years ago, and it's famous for its use as a flocculant and its ability to grow large, beautifully clear crystals. Now, I have tried growing really big alum crystals a few times before, but it really does require an absolutely insane amount of patience, which I admittedly lack. If you'd like to try it yourself, the basic procedure involves simply tying a small seed crystal of alum on a string or wire and then submerging it into a saturated mixture of dissolved alum. In theory, all you have to do then is wait for the water to slowly evaporate, which will begin to slowly grow your alum crystal. In practice, however, I found that ambient temperature, humidity, and pH all play a huge role in crystal growth, and with all these variables just to grow a crystal and so many other projects on my plate, I've never grown a terribly impressive alum crystal. But there is a subreddit dedicated to some truly impressive ones if you're interested. Anyway, proper alums have a very distinct octahedral structure, and can only form by coordinating to 12 molecules of water. Broadly though, an alum can be any hydrated or anhydrous double salt of a monovalent cation and a trivalent cation with sulfate. This implies a whole lot more flexibility than there really is in practice, and to try and explain what I mean, let's take a look at the periodic table. Here first, I've tried to highlight every element reasonably capable of forming a monovalent cation, which in theory could all be used to make an alum. However, the group 11 metals copper, silver, and gold are either unstable or insoluble as monovalent sulfates, and so not really feasible in practice. In addition to being stable and soluble as a sulfate, the monovalent cation used in an alum must also be an appropriate size. Hydrogen, lithium, and sodium are too small to form alums, and thus again not really feasible. Cesium and rubidium do form alums, but they almost do it too well. Their atomic radius is so big that they end up forming alums that are nearly completely insoluble, which is awesome for selective precipitation, but not great for growing nice, beautiful, clear crystals. To try and show you what I mean, here's a clip from a recent video I made extracting cesium from a rock. In this clip, you can see me pour a boiling hot mixture of saturated cesium alum into a beaker, which immediately begins to crystallize. After about an hour, virtually all of the alum had completely crystallized out, with this rapid process forming tiny, unimpressive crystals. With that said, even though cesium and rubidium alums are fascinating in their own way, since I'm going for big, impressive crystals here, I went ahead and eliminated them along with thallium for obvious reasons. With that, my only viable option for a monovalent cation was potassium along with ammonium, which is what I mean when I say there's a lot less flexibility in practice than in theory. With the monovalent component settled, let's turn now to the trivalent component. Here again is every element capable of reasonably forming a trivalent cation. As you can see, there's quite a few of them here, so there was seemingly a lot more flexibility here in my choice of trivalent ion compared to monovalent. To try and trim this down a bit, I first eliminated scandium, molybdenum, cobalt, manganese, ruthenium, rhodium, gold, and iridium, as these elements are either too expensive or basically impossible to stabilize in their +3 state. Thallium was eliminated again for being incredibly toxic, and both antimony and bismuth were eliminated as their sulfates tend to easily hydrolyze, which felt like it would be annoying to deal with. Looking now at the lanthanides, lanthanum, cerium, gadolinium, ytterbium, and lutetium were eliminated as their trivalent salts are colorless or kind of a boring yellow, and I'd kind of just expect them to look like a very expensive aluminum alum in a best case scenario. And lastly, promethium was eliminated because it doesn't really exist for all intents and purposes. Now, after having gone through the entire periodic table, I was left with the following possible alums. Very few of these really worked, and the ones that did each presented their own difficulties that made this a true test in perseverance. And with that, it was finally time to get started, and I figured that the easiest place to start would probably be with iron. I ended up trying two different routes to make an iron alum, and for the first, I began by adding 30 grams of iron 2 sulfate to a beaker, followed by 6 milliliters of 98% sulfuric acid. Normally I'd add the acid after dissolving the iron 2 sulfate, but I thought it would be fun to watch the acid dehydrate the iron sulfate to the white anhydrous form. Anyway, I next added about 30 milliliters of water, which was enough to dissolve most of the iron sulfate and get everything moving freely. I next began to add 70 milliliters of 6% hydrogen peroxide to the mixture under constant stirring. This will oxidize the iron 2 sulfate to iron 3 sulfate, and must be done slowly as the reaction can easily get out of control. Once all the peroxide had been added, I moved the beaker in front of a light so you could more easily see the color of the dark mixture. Meanwhile, in a separate beaker, I dissolved 8 grams of ammonium sulfate in 80 ml of water, and then combined it with my acidic iron 2 sulfate. This is done to provide ammonium as a monovalent cation for the alum, and the sulfuric acid was added earlier to help stabilize the iron 3 sulfate. Once I'd given this a few more minutes to mix, I went ahead and poured it into a large crystallizing dish and set it aside to allow the alum to form. Now, because I had so much volume here, it did take a while for the alum to form, but you can speed it up if you'd like. This is most easily done by gently heating the mixture on a hot plate. However, if you do this, it's important to confirm that the temperature never goes too high. This is because elevated temperature can hydrolyze the iron and prevent it from forming an alum. Hydrolysis can be indicated by the color of the mixture, and you want a black tea color while a rust orange indicates hydrolysis. Now, my second method for making an iron alum was a whole lot less quantitative, but I found that it honestly worked a whole lot better. For the second run, I began by first dissolving some steel wool in dilute sulfuric acid, and this will form iron 2 sulfate, which is what I started with in my last run. Now that I'm watching this clip here, I'm noticing that it looks like I used hydrochloric acid instead of sulfuric acid here, but it really doesn't matter at all what acid you use, you just want to dissolve the iron for this step. Once all the steel wool had dissolved, I passed the mixture through a coffee filter to remove all of the insoluble carbon that had precipitated. I then returned the mixture of iron 2 sulfate to the beaker, followed by about 30 milliliters of 30% hydrogen peroxide. This is done to oxidize most of the iron 2 sulfate to iron 3 sulfate, but because none of this is quantitative, I definitely didn't use enough here. Anyway, at this point, I went ahead and transferred the beaker to my stir plate and began to slowly neutralize my mixture with 5 molar potassium hydroxide. This immediately precipitated a black mess of hydrated iron 2 and 3 oxides and hydroxides, but I kept going until the pH was over 12. I then added a large excess of 10% sodium hypochlorite bleach, and this was done to confirm that all of the precipitated iron was in the trivalent state. This was rinsed thoroughly by adding a massive excess of water, allowing the black iron hydroxide to settle, and then decanting the excess water off the top. I ended up repeating this 4 different times until there was no detectable smell of bleach, and then collected the iron hydroxide in my Buchner funnel. After most of the water had been pulled off, I next transferred the black paste to a beaker along with around 175 milliliters of 50% sulfuric acid and allowed the two to react under constant stirring until most of the iron hydroxide had dissolved to iron 3 sulfate. To this, I next added enough 5 molar potassium hydroxide to bring the pH up to around 3, and then filtered the mixture again to remove any undissolved iron hydroxide. I went ahead and gave it a quick final mix, dumped it into my crystallizing dish, and then set it aside to allow crystals to form. By the next day, small crystals began to form in both dishes, and by day 7, crystals covered the entire bottom. By day 10, I felt most of the growth was done and decided to collect my crystals of iron alum. When I decanted away the solution to reveal the crystals, I was somewhat surprised that they weren't yellow or orange like I'd expect from a trivalent iron compound, but a very faint pale violet color. I got a lot of really great footage of these crystals, but in the interest of time, I put most of that footage later in the video. Iron alum was pretty weird, and had the tendency to quickly turn orange when exposed to air. It also formed an orange mixture when dissolved in water, but returned to its violet color as soon as the water evaporated. Here I got a good recording of what it looks like to dissolve iron alum in water at the test tube scale. As you can see here, the violet crystal quickly dissolves to the black tea color, which converts to the rust orange when strongly heated. In addition to being quite beautiful, I think this alum would make for a good source of solid trivalent iron, as most trivalent iron compounds tend to be extremely soluble and thus pretty tough to store as solids. Industrially, the only trivalent iron compound that's widely sold is iron 3 chloride, and it's most often sold as a concentrate. In regard to some ways you could try and streamline this process, chlorine might be a good option to oxidize the iron 2 sulfate to iron 3 sulfate. This would avoid you having to go through a ferric hydroxide intermediate and avoid the problem of the added volume and possible hydrolysis posed by using peroxide. However, I will admit this option is a little bit unnecessarily dangerous given the alternatives. Potassium persulfate could work too, and I did have some success using nitric acid as an oxidizer. Anyway, moving right along, I next tried chromium alum, which was a lot tougher than I expected it to be. My original strategy was to simply dissolve some chromium 3 oxide in sulfuric acid, filter off any that didn't dissolve, and then partly neutralize using potassium hydroxide. However, this simply left me with a somewhat viscous green mixture that refused to crystallize at all, even after being left for a month. After doing a bit of research, I found that trivalent chromium ions tend to form an extremely soluble complex with sulfate upon heating above 40 degrees Celsius. In order to form a proper alum, both chromium 3 ions and sulfate ions would need to exist independently in the mixture and both separately coordinate to water as they crystallize. As a result, the chromium sulfate complex will never form an alum. Allegedly, over a long enough timeline, the sulfate ligands do release as free sulfate, which would allow an alum to form, but I've personally never seen this happen. In any case, I now needed to think of a way to make a solution of chromium 3 ions, sulfate ions, and potassium ions without ever exceeding 40 degrees and forming the complex. To this end, the best I could come up with was to reduce potassium dichromate in excess sulfuric acid using ethanol. To do this, I first dissolved 20 grams of potassium dichromate in a minimal volume of distilled water, followed by 16 milliliters of 98% sulfuric acid. I went ahead and added a few ice cubes to the mixture before slowly adding cold ethanol to begin the reaction. As soon as the ethanol was added, the mixture immediately darkened as the dichromate oxidized it to acetaldehyde, itself being reduced to chromium 3 sulfate. This reaction is really exothermic, so it was carefully cooled to keep the reaction from getting too hot and forming another useless green goo. The byproduct acetaldehyde is also a very powerful carcinogen, and so care must be taken not to inhale any. Also, if you weren't already aware, dichromate is extremely toxic and highly carcinogenic as well. I do recognize here that I allowed the temperature to go well beyond 40 degrees Celsius, and that did definitely hurt my yield. I really should have cooled everything here down to at least freezing, but again, I have a hard time waiting. Regardless, once I had added a total of 15 milliliters of 95% ethanol, the reaction was complete, and already some crystalline sediment had started to crash out. I then allowed the mixture to rest overnight to precipitate as much as possible before passing all of this through my Buchner funnel to collect my crude crystals of chrome alum. To my surprise, these were once again violet colored, which was really weird for the typically green trivalent chromium. The chrome alum, though, was far darker than the iron alum and appeared nearly black depending on the lighting. These fine crystals were redissolved in a minimal volume of room temperature water, which was then poured into a crystallizing dish to allow it to slowly evaporate and form larger crystals. After another week, some far larger crystals of beautiful chrome alum had formed, which I collected in the same way I did the iron alum. Chrome alum seemed to be a lot more stable than the iron alum and didn't look any different after a week being left uncontained. When dissolved in cold water, it forms a bluish-violet mixture and turns a deep green upon heating above 40 degrees Celsius. Once it turns green, it's no longer able to crystallize, as I mentioned earlier. Once again, I got some pretty good recordings of these color changes at the test tube scale, which I think look really cool. You can also form a unique violet complex of ammonia and trivalent chromium by dissolving the chrome alum in a bit of water and then adding concentrated ammonia. As soon as ammonia is added, the mixture turns a distinct violet, and when heated at this point, the color actually intensifies rather than the whole thing fading to green. This happens because ammonia coordinates more strongly to chromium than sulfate does, and so this complex is actually quite stable. However, if ammonia is added after the trivalent chromium has been heated to its green form, the complex will no longer form. Another fun thing I decided to try was dissolving 1 part chrome alum and 10 parts aluminum alum in some water and then allowing it to evaporate slowly. As I had hoped, this ended up forming far lighter violet crystals, which made the color a lot easier to see. As with the iron alum, I think this is possibly a good source of solid trivalent chromium, which otherwise has a tendency to be super soluble. The next alum I decided to try was vanadium, and it was interesting if nothing else. To make vanadium alum, I began with vanadium pentoxide, which represents vanadium in the +5 state. This was first reacted with potassium hydroxide to make potassium vanadate, which is a water-soluble salt similar to potassium chromate. This was next acidified using concentrated sulfuric acid until the mixture had turned a deep orange. This orange mixture is typically clear when using a much more dilute potassium vanadate, but as you can see here, that was very much not the case. I got a pretty dense precipitate to form in this step, and I'm guessing that's simply because vanadium 5-sulfate is not that soluble. At this point I simply added some ethanol and allowed the mixture to sit and react for a while. Over around the next 30 minutes, the ethanol eventually reduced the pentavalent vanadium to the brilliant blue vanadyl sulfate representing vanadium in the +4 state. This reaction happened so slowly that I did decide to cut it, but I did include a more dilute version of this reaction later in the video if you want to hang around to see that. To make this into an alum, I then needed to further reduce it to the +3 state, which I had wanted to do using a non-metal reducing agent in order to limit contamination of my vanadium alum. Sadly though, I couldn't find any reducing agent that worked here, so I decided to go with the tried and true zinc reduction. When you add metallic zinc to a blue mixture of vanadyl sulfate, it'll first slowly reduce it to the extremely dark green vanadium 3 sulfate, and then to the violet vanadium 2 sulfate. Because my mixture here was so dark and concentrated, it was really hard to see when it had been fully reduced to the +3 state, so there is a chance I went too far or not far enough. Regardless, at this point I went ahead and stoppered my flask up, as oxygen in the air will slowly oxidize both divalent and trivalent vanadium compounds back to the blue vanadyl sulfate. I then set it on my desk overnight to hopefully crystallize out some vanadium alum. When I came back the next day, I found a few deep purple crystals had formed, but I felt like the quantity was a bit low for how much vanadium I used here. Reasoning that perhaps I simply didn't reduce the vanadium enough, I added more zinc along with a bit more sulfuric acid and heated the mixture strongly until it had turned a uniform dark purple. This was again stoppered and let to sit on my desk overnight to crystallize. This time when I came back the next day, I was greeted with a far larger mass of crystals, which as you can see covered the entire underside of the flask. I went ahead and first started breaking these up so I could get them out of the flask, and then collected them in my Buchner funnel. I used a vacuum to pull off as much liquid as I could, and then dumped them onto a paper towel to dry. After then dabbing the crystals as dry as I reasonably could, I transferred them to an airtight jar for storage, and this is because I didn't want them reacting with any oxygen in the air. As a quick check-in, here are all the alums I've made so far. As you might remember from earlier, the iron alum is a very faint violet, while the chrome alum was an exceedingly dark purple, appearing nearly black at a distance. This vanadium alum, however, seemed like a perfect in-between the two. Unlike the other two alums, this one doesn't really dissolve in water. Instead, trying to dissolve the vanadium alum only results in the mixture becoming a cloudy light yellow mess due to the presence of the barely soluble vanadium 3 sulfate. However, a number of chemicals can readily oxidize this back to the highly soluble +4 state, which I show here with a few drops of 67% nitric acid. With vanadium alum complete, there is now only one transition metal alum left to try, and that was titanium. I held off on trying titanium until last, as I figured it was either flatly impossible or very difficult in a best case scenario. This is because titanium is very difficult to dissolve, and even when it does finally dissolve to aqueous ions in the +3 state, it then readily reacts with oxygen in the air to the +4 state. Not only that, but literature on trivalent titanium compounds is scarce, with not so much as a Wikipedia page on titanium 3 sulfate. Regardless, I felt like I had to give it a try, and so to get started, I began by adding a small scoop of titanium powder to a flask, followed by a bit of water. I then added a few milliliters of sulfuric acid, which produced enough heat as it was added that the titanium began to dissolve. This began to quickly form the deep violet titanium 3 sulfate, which is a lovely color if nothing else. As a quick final step, I added some ammonium hydroxide to partly neutralize the sulfuric acid and to provide a monovalent cation for the titanium alum. The flask was then loosely capped and placed on my hot plate to sit around and react at low heat for a few hours. It's important that the stopper is only loosely placed here so that all the hydrogen gas produced by the reaction can escape while not easily allowing any air to get in. Eventually I moved this all to a bigger flask, and after being allowed to react for a few hours, I decided to take the flask off the heat and allow my titanium alum mixture to cool. Once it had sat overnight, I decided to go ahead and dump the mixture through my Buchner funnel to collect any crystals that might have formed. As you can see, nearly everything passed right through the filter, but it was able to catch a tiny amount of these light purple crystals along with the remaining undissolved titanium. I'm not actually positive whether these crystals are titanium sulfate or titanium ammonium sulfate, but in either case, they definitely weren't big crystals of alum. At this point, I basically figured that pure titanium alum wasn't really possible, but before I gave up completely, I decided to try one final thing. My idea here was to basically do the same thing I did earlier with the chrome alum and dissolve a large excess of regular aluminum alum into the mixture of titanium alum. My hope was that maybe as the aluminum alum crystals formed, some of the titanium alum would incorporate itself into the crystal structure, resulting in some nice light purple crystals of at least a partly titanium alum. I let the mixture of dissolved titanium and aluminum alums crystallize in a sealed flask overnight, and when I came back the next day, I simply tried breaking up whatever crystals might have formed and then dumped the whole thing through my Buchner funnel. As you can see here, the resulting crystals were a dark violet, with this color remaining even after the crystals were thoroughly rinsed. With that, I do feel it's safe to say that the titanium alum was incorporated at least to some extent into the structure of the aluminum alum, although I can't say I'm terribly impressed with the crystal structure. Remember earlier when I said that pH had a significant impact on crystal growth? Well, more specifically, very low pH causes an alum to form as much smaller, irregular crystals that aren't very impressive to look at. The problem here is that not only is titanium alum unstable in open air, but it's also insoluble without a significant excess of sulfuric acid. Without being able to bring this up closer to neutral or slowly evaporate a saturated solution in open air, I unfortunately don't really see any practical way to grow a nice crystal of titanium alum. Anyway, here are all my transition metal alums, and weirdly enough, they're all some variant of violet. I'm not really positive why that is, but I figured it was worth noting. Now, before I move on to the lanthanides, I'm going to give myself a moment to catch my breath, because that was basically one really long recording session. In the meantime, I'll go ahead and play a minute or two of crystal footage I got earlier and didn't have time for. If you want to skip this and go ahead and move on to the lanthanides, feel free to skip to the time shown on screen. Welcome back. Now, with all the viable transition metals complete, I decided now to move on to the lanthanides. To this end, I began by dissolving some Neodymium, Praseodymium, Europium, Terbium, Holmium, and Erbium metal from my element collection in dilute sulfuric acid. For the most part, this wasn't a big loss as many of these samples were improperly stored and had already begun to oxidize. Honestly though, even if they were fine, dissolving these collectible samples from element sample suppliers is by far the cheapest way to get lanthanide salts. Anyway, dissolving all of these element samples was actually pretty easy, and the only extra step I had to take was adding a bit of hydrogen peroxide to the europium sulfate. This is because europium sulfate tends to form as a divalent cation, which is structurally very similar to barium sulfate and thus very insoluble. Once each of these had completely dissolved, I next filtered them to remove any stubborn particles and began trying to make them into alums one by one. I tried neodymium and praseodymium first, and my strategy this time around was to first add potassium hydroxide until the metals had completely precipitated as their respective hydroxides. I then slowly added sulfuric acid until the hydroxide had redissolved in order to obtain a solution containing all the right ingredients for an alum to form. However, with these first two, as well as with europium and terbium, a very fine precipitate immediately formed as soon as the hydroxide had redissolved in the acid. At first, I didn't really think this was a problem, as I figured I could simply redissolve the sediment by heating and then allow it to slowly cool and form proper alum crystals. However, what I very quickly realized is that every single one of these lanthanide sulfates exhibit the otherwise very rare quality of retrograde solubility, becoming less soluble as temperature increases. This could honestly be a really good way to separate rare earth sulfates from complex mixtures, but for alum crystal growing, it's very much not ideal. This left me with no option but to continue adding cold water until eventually the salt dissolved, but even this didn't work very well. The terbium and europium salts did eventually redissolve in an absolutely absurd volume of water, but considering the much larger quantity of neodymium and praseodymium salts I made, these two were never going to redissolve in any reasonable volume of water. Regardless, after I had dissolved them all as much as I feasibly could, I went ahead and allowed the mixtures to slowly evaporate, hoping that eventually some type of alum might form. Sadly though, after over 2 weeks of waiting, I had nothing to show for it and decided to give up. It seems that although these four lanthanides will readily form double salts with potassium, they don't readily form dodecahydrate complexes with water. This also seems to be true of other compounds I've made that exhibit retrograde solubility, and so I think that lanthanide alums are simply impossible. In case you forgot about holmium and erbium, these two are weird in that they didn't form any precipitate when treated with potassium, nor did they form any alum when allowed to evaporate. And with that, the lanthanide alums were a total wash, but not a total loss. The amazing optical properties of these lanthanide sulfates were so incredible and previously unknown to me that this whole process spun off into a project of its own, which you can check out if you're interested. Now, with the bottom of the periodic table cleared out, I decided to wrap this up with the alums that, while possible on paper, didn't really seem worthwhile to make. As a reminder, these included the post-transition metals Gallium and Indium, as well as the transition metal Yttrium. Now, the first problem with trying to make alums out of these elements was the cost. Each of these elements are quite expensive, with indium in particular being significantly more expensive than silver. The second problem with all these elements is color, with all of them forming exclusively colorless solutions, meaning that in a best case scenario, they would basically just look like very expensive aluminum alums. The final problem here is hydrolysis, which I'll get into more in a second. In the meantime, my strategy for making the indium, gallium, and yttrium alums was the same as the lanthanides. Basically just dissolve the pure metal in sulfuric acid and partly neutralize using potassium hydroxide. These all seemed promising at first, but after allowing the mixtures to slowly evaporate over the course of the next week, it became clear that I wasn't going to get what I wanted out of any of these elements. Gallium was the first to fail, with the barely soluble gallium sulfate quickly precipitating out as a fine powder soon after the solution cooled. The other two might have indeed formed alums, but after a week I was not able to spot even the tiniest crystal growing. That said, the alums formed by indium and yttrium were likely more in line with holmium and erbium from earlier. Since these three alums were basically a wash as well, I went ahead and just precipitated them as their hydroxides and stored them for some unknown later project. And with that, after months and months and months and months of work, these 4 alums are all I was able to make. I still do consider this all worthwhile though, as I didn't know that any of these would be possible at all, particularly the vanadium and titanium alums. Not only that, but this project spawned 4 other projects, one of which I've already made a video on, and the others I'm working on wrapping up. The one I already released was the previously mentioned video on lanthanide salts, but realizing that I could dissolve bulk scale titanium was critical for a video on aqueous titanium chemistry and the pigment titanium white. The last project that spun off of this one is on another category of crystalline double salts called Tutton salts. Tutton salts are very similar to alums, with the main difference being that the trivalent cation is replaced with a divalent cation. The most famous example of a Tutton salt is likely Moore's salt, which is ferrous ammonium sulfate. Considering how many highly stable divalent cations exist, I was able to make far more Tutton salts than alums, so definitely keep an eye out for that video if you're interested. On a final note, I do want to quickly say that there is a chance that the vanadium alum I made could in fact be the divalent Tutton salt due to excessive reduction by zinc. I've never been able to find a photo or physical description of either vanadium-2 or vanadium-3 potassium sulfate, so without a reference, I'm honestly not 100% confident in what I made. I did try leaving the violet vanadium alum out in the open air for a few weeks to see if it would eventually oxidize to a new color, and this is what it looked like at the end. It definitely lightened up a bit, which tells me that maybe this is true vanadium alum and what I had earlier was the divalent Tutton salt. I still don't really know for certain, so if somebody out there happens to have this absurdly obscure piece of information, I'd love to hear about it in the comments. All in all, if I'm completely honest, I don't think there ever would have been a point in this project, no matter how long I spent on it, where I was entirely happy with everything I made and totally confident about all my products. The overwhelming number of variables here, constant problems with hydrolysis and solubility, and just general lack of any literature on most of what I did here made it kind of a nightmare at times. As I said though, I do think it was all worth it, and if nothing else, I hope this video is a good starting off point for someone else who wants to make their own exotic alums and hopefully do a better job than I did. Anyway, that's all I've got for today. Feel free to stick around for some extra footage I got of the crystals and for a much more dilute reduction of the vanadium where you can actually see the color shift. With that, I hope you found this interesting, and as always, I want to thank all my members here on YouTube for your generous contributions. Your support is vital and very appreciated. To everyone else, if you'd like to see more content like this, consider subscribing here or on TikTok or even by becoming a member yourself. Thank you all so much for watching, and I'll see you next time.